Simulation study on the effect of skew on comparison of means tests. Central question in many fields is if groups A and B are different. Three common tests to check this are the t-test, with and without the assumption of equal variance, the randomization test, and the Wilcox-Rank sum test. An important question to ask is when are each of these tests most appropriate? I'll be looking at the effect of skew from the population on the power of each of these tests across a range of sample sizes. T-test is a standard comparison between two means in many fields. It assumes that the populations have normal distributions, and there are two variants which I'll be looking at, one which assumes equal variance and one which does not. Randomization test is much more computationally intensive. It simulates 100,000 or more times, randomly allocating all of the observed units into the two samples, and it calculates how often the difference of those two samples is equal to or greater than that observed. This test assumes equal variance and is useful for small sample sizes. Wilcox-Rank sum test is a less computationally intensive version of the randomization test. It orders all of the observed units and assigns a number to each. Using these new values for each of the units, it calculates the likelihood of the observed difference happening. This test discards information from the sample by ignoring the magnitude of difference between each of the observed data points, and is potentially less sensitive to outliers and skewness. The distributions I'm looking at are the normal distribution and the normal square distribution. You can see here that normal square distribution is slightly right skewed. I'll be checking the difference of means of 0, 1, and 2 standard deviations. 0 to check the type 1 error, 2 as a control to make sure that the simulation is working, and 1 standard deviation pictured on the left to look at the power across the range of sample sizes. An important thing to remember is that the sample is drawn from the population and will not recreate it perfectly. If you sample a population repeatedly, the distribution of sample statistics will form a normal distribution centered at the population parameter. Here you can see I sampled 100,000 times from two different normal distributions, but I have a difference of means of 1 standard deviation. If your sample is larger, then the variance of these distributions will be narrower. Going from a sample size of 10 above to 100 below, you'll see that the likelihood of being unable to distinguish the difference between these two populations decreases as sample size increases. For the simulation, I'll be looking at 3 explanatory variables: the sample size ranging from 5 to 50 per group, the difference of means of 0, 1, or 2 standard deviations, and the normal and the normal square distributions. For each of these variables, I generate 2 random samples, perform all 4 comparison tests on those 2 samples, then I repeat this 10,000 times. Then calculate how many of these iterations produce a p-value of 0.05 or less, which corresponds to rejecting the null hypothesis. Looking at the data, the type 1 error rate is approximately 0.05. For each of the conditions in the test, it ranges from 0.028 to 0.054, all of which are very close to 0.05, which corresponds to the expected 0.05. Looking at the normal distribution, all of the tests are comparable, with the Wilcox-Rank sum test being slightly less powerful at sample sizes smaller than 30. Going to the normal squared distribution, all of the tests are similarly powerful to the normal distribution when sample size is 10 or larger. All the tests perform comparably, including the Wilcox-Rank sum test. Important things to conclude are that the type 1 error is the expected of 0.05. When the difference of means is 2 standard deviations, the power is 0.98 or higher, as long as the sample size is 10 or larger. All 4 tests perform comparably on both normal and normal squared distributions. The Wilcox-Rank sum test does perform relatively better on slightly skewed data than normal data, which could support the idea that it is less sensitive to skew. Takeaway from this simulation study is that when 2 samples have equal variance and are not overly skewed, these 4 tests are equivalent. Increased skewness beyond normal squared could segregate the tests, could make them have different results. In addition, I did not look at unequal variance or sample sizes, and those could also affect the appropriateness of each of these tests. I'd like to thank Professor Kuiper, Samantha Mizuno, and Toby Barada, along with Grinnell College, for their guidance and support doing this work. The code and data that I use can be found at these links. Thank you.